Hello, welcome. Today's lecture is going to cover a new topic. We're going to talk about operational amplifiers. Operational amplifiers are an interesting device. They differ from elements that we've talked about in the past, such as resistors, capacitors, and inductors, because in fact, operational amplifiers are not directly made out of, resistive materials or by using, let's say, two parallel plates or a coil. Physical materials to create the element. Operational amplifiers are actually just an abstraction for a circuit that behaves a certain way. The symbol that we usually use to represent operational amplifiers is a triangle, such as you see on the left side of the slide here. Notice that there are 5 different nodes around the triangle which have been defined. V plus and V minus are power supplies. One is a positive supply, the other is a negative supply. These indicate essentially the rails which bound the output of the operational amplifier. So in other words, the output, indicated by node 6, always has to reside between whatever values V plus and V minus are. This is indicated in the plot to the right-hand side if you consider that the output voltage is now leveled off once you get beyond a certain input. It should be noted that the actual value of V minus does not necessarily have to be a negative voltage. You could, for example, ground V minus and have V plus set at 5 volts, or you could have V minus set at 3 volts and have V positive set at 8 volts. But if you did that, your output would then be bounded between 3 volts and 8 volts. We have 2 inputs on the operational amplifier. One is called an inverting input and is usually labeled with a minus sign on the inside corner of the triangle. The other is called a non-inverting input, which is then labeled with a positive sign on the corner of the operational amplifier system. If you look at the way that operational amplifiers behave, we can define their behavior in terms of 3 regions. Operational amplifiers are a special kind of amplifier which is used to boost the gain of your input voltage. However, they're what's called difference amplifiers, meaning that the output is a function of the difference of the 2 inputs. So this is why on the x-axis of the transfer curve for the operational amplifier, we have listed Vp and Vn, which are the positive or non-inverting input voltage value, minus the value Vn, which is the inverting input voltage value. So my output is a function of the difference of the 2 inputs. And when it's operating in what's called the linear region, the amplifier provides some amount of gain on this difference, giving you an output. Now, the values of the supplies, which are also oftentimes labeled as VCC and minus VCC, bound the amount of gain that you can really get on the amplifier. If, let's say, the value of your plus and minus VCC was plus and minus 10 volts, and you had an input which, when you multiplied it by the gain of the circuit, it actually exceeded those values, then the operational amplifier is going to force the output to stay bounded by whatever the value of the positive and negative supply voltages are. This is why the curve in the transfer characteristic levels off beyond a certain point in the positive and negative direction. If you have a situation where your output voltage is being bounded by the supplies, this is termed as saturation. The term saturation basically says that you're not able to get as much gain out of the device as you would normally get because you've now encountered a bounded situation. There's a positive saturation region, which is the case where the positive supply limits the output, and there is a negative saturation region, which is the case where the negative supply limits the output. The actual circuit for an operational amplifier is beyond the scope of this class. I'm going to briefly just show you what the schematic of it is, not that I really expect you to be able to follow it. The circles are basically transistors. We haven't covered transistors in this class, but they are a special type of semiconductor device which you can build more complicated outputs of. And essentially, the combination of all of these elements that you see in this circuit is resulting in the gross behavior, which we've kind of just schematically drawn for you on this previous slide. Because this circuit is somewhat complicated to analyze, oftentimes we use models to greatly simplify our circuit analysis of this device. One common model that's used is what's known as the two-port model. And in the two-port model, we still have the same inputs that have been defined on the more abstract symbol on the previous slide. We have our output, Vout. We have V1 and V2, which are at the inverting and non-inverting inputs of the amplifier. We also have our supply voltages, the positive supply and negative supply. But we are going to model the behavior of this amplifier using a dependent source. Our output voltage, Vout, is going to be equal to some gain, A, times the difference of the two inputs, V2 minus V1. This is indicated by the source that has a sine wave in it in the middle of this triangle, which represents the op amp. We're also going to model the input and output resistances using the labels Zin and Zout. Note that if you wanted to actually calculate what Zin and Zout were, in the original circuit, you would simply find the Thevenin input resistance as seen from the two input terminals, V1 and V2. And to find the output resistance, you would look at what Thevenin resistance you get by this time looking at the output node and ground. So the concept of Thevenin here is I hope, very helpful in terms of aiding you into seeing why we might want to use a model like this to represent the behavior of the op amp. If you actually wanted to use this model in a real op amp problem, then you would simply replace the triangle that's shown in the circuit with this combination of two resistors and a dependent source, and use the same Kirchhoff analysis techniques that we've been doing so far since the beginning of the semester. We're going to actually use in this class a simpler, even more idealized model to be able to get gross operational amplifier behavior, but I still wanted you to have an initial look at the two-port model for the op amp in case you came across it in your later studies. Typically, operational amplifiers are designed such that the gain A, which is known as the open loop gain because currently we don't have any feedback connection between the output and the input. So the open loop gain is usually extremely high. It's on the order of at least 100K to even over 100 million. So we're talking about a really, really steep slope on that transfer characteristic curve that I've showed you below. The input resistance is also exceedingly high. It's on the order of 10K to even tens of thousands of mega ohms. If you remember our discussion in class earlier in the semester, when we talked about voltage dividers, you might remember that we talked about the effect of loading on our measurement of voltage parameters. The reason for why we design operational amplifiers to have such a high input resistance is so that when this input resistance acts as a load on any circuit that we might connect to its input, it will have a very minimal effect on the behavior of whatever circuit precedes the operational amplifier. The output resistance, in contrast, is designed to have a very, very low input resistance on the order of several tens of ohms, at most 100 ohms. Voltage supply values can vary, but typically they have a magnitude of 5 to 24 volts. It really changes depending on the model of op amp that you're trying to use. In this class, what I want to do is just show you how we can solve and analyze some simple amplifier problems by using what's known as the ideal op amp model. So I want to give you a little bit of a motivation for this model first. On the left-hand side, you see the transfer characteristic that we discussed below. And you can see that it has a slope A, which, as I said, is very, very steep. So one approximation that we could make is we can just say, okay, well, let's just assume then that our slope is infinite, as shown on the right-hand side curve. And then you have just a clean discontinuity between the positive and negative saturation regions. If you make that assumption, then essentially what you're also saying is that the difference between the two input voltages is negligible. So essentially the positive non-inverting input and the negative inverting input, you're saying they essentially have the same voltage values being provided on the input. So one motivation I can give for that is if you actually plug in some sample values and consider, for example, what the difference between VP and VN would be if you had a 50-volt difference between your positive and negative supplies divided by a gain of 10 to the 5, then the difference between VP and VN would only be half a millivolt, which is very small. And in most practical circuits, that's on the order of the noise, the electronic noise that you would see in your system. The current that's drawn under those conditions can also be approximated by just taking the input voltage and dividing it by the input resistance. Now, this is just a kind of back of the envelope calculation here, but it gives you an idea of the order of magnitude. And if you take half a millivolt, divide it by an input resistance of, let's say, 10 or 100 kiloohms, then you get something on the order of 5 nanoamps. So that's an extremely small input current. As a result, the ideal op-amp model states that when the op-amp is operating in the linear region, we can assume that essentially there's no current being drawn in on the input and that the voltage values at the two inputs are equal. Let's see how now we can apply that to an example for actually analyzing a basic amplifier. This is an amplifier circuit that's known as an inverting amplifier for reasons that you'll see once we derive the transfer characteristics. The circuit, at the core of the circuit, is the operational amplifier, where I've labeled the inverting and non-inverting inputs with the minuses and pluses. We have a positive supply of VCC and a negative supply of minus VCC. I have my output voltage here, V out, and I'm going to take the positive input and tie it to ground for this particular circuit topology. And I'm going to apply feedback from the output back to the inverting input. So this loop that I've just drawn represents a feedback loop, hence my labeling of the resistance as RF. And I'm also going to connect that to a source resistance, RS, which is then connected to some voltage source, VS, which is on the input. So this is the topology for my inverting amplifier. And what I want to do is just show you step by step how we can apply the ideal op-amp model to solve this problem. So what are the basic steps? The first step is you have to find an expression for V positive. V positive is the symbol that I'm going to use throughout the semester for the value of the voltage at the non-inverting input. Similarly, I'm going to use the symbol V minus for the value of the voltage being supplied to the inverting input of the op-amp. And we're going to use nodal analysis to find V positive, another set of nodal analysis to find V negative, and then finally, we're going to enforce the condition that V positive equals V negative. And in doing these steps, we're also going to make sure that we take the current coming into each of the inputs as being 0, because those are our main assumptions when we use the ideal op-amp model. Our first assumption is that the voltages on the inputs are approximately the same. And our second assumption, if you remember from the previous slide, was that I plus equals I minus, which equals 0. And so as long as we enforce these two conditions, we can apply the same theories that we've learned before for solving the problem. Now note that this solution assumes that we are in the linear region. Without actually solving the circuit, we do not know ahead of time whether or not we are in the linear region. So we are going to start by assuming that we are in the linear region, and we are going to solve the problem based on that assumption. But thereafter, we always have to go back and then check our assumptions to make sure they're not violated. So now let's go through and just solve the circuit. Since I've grounded the positive terminal, the positive input of the operational amplifier, the first step is pretty simple. V plus is equal to 0 volts. Now in the second step, we have to actually calculate what the input voltage is. And what I'm going to do is I'm going to apply the node voltage method with KCL at the negative terminal here. And so you have 0 plus V minus minus Vs divided by Rs plus V minus minus V out divided by Rf. And all that has to sum to 0. So let's translate this to this side. We have V minus minus the input divided by the input resistance plus V minus minus the output voltage divided by the feedback resistor plus 0, because we're assuming that no current is actually going into the op-amp itself, is equal to 0. And if you kind of go ahead and just do the mathematics for solving and rearranging this problem, what I want to do is I want to isolate V minus. So I'm going to solve in this equation for V minus. I can find that V minus is equal to RF divided by RF plus RS times the input voltage plus RS divided by RF plus RS times the output voltage. And now I've finished the step of finding for V minus. The last step is to say that the two input voltages have to be equal to 0, which, since V positive is equal to 0, this means that V negative must also equal to 0. So I'm going to take the same equation that I had before. Let me just copy it over onto this slide. And I'm going to equate it equal to 0. And if you do this, you can see that we've now achieved an expression which is only in terms of the input Vs and the output V out, which you can solve for to find what's known as the transfer function. The transfer function relates the output to the input. I'm going to write that as a ratio. And if you do this, then you'll find that you get minus RF divided by RS. This ratio is essentially your gain. What I mean by the gain is it's the scaling factor by which your input is now being amplified to get your output. And if you look at this particular equation, you can see that there's a minus sign out front. This is why this is known as an inverting amplifier. And the ratio of RF divided by RS is telling you how much you actually boost the circuit. So if you want to, for example, have a circuit which doubles the amplitude of your input, then you would pick resistor values such that RF was twice as large as RS. Now remember, the last thing that we need to do is we have to make sure that we are in the linear region. So this expression is only valid so long as V out is between the positive and negative power supplies. What happens if V out exceeds these limits? Well, the circuit will clamp the output in either positive or negative saturation, depending on which limit is the one that's being violated. So let me give you some numbers to just show you an example of this. Let's suppose that VCC is equal to 15 volts. And let's suppose that RS is equal to 5K ohms. RF is equal to 10K ohms. This gives us a ratio of RF to RS of 2. So we're boosting it by 2, but we're also flipping the signal because we have a negative sign in front. Let's assume that our input voltage, Vs, is a sinusoidal function. Let's say it's 5 sine omega t, where omega t is some frequency. I'm not concerned with its value at this point. What would be the output of this amplifier? It would be whatever the input is times minus 2. So it would be minus 2 times 5, which gives us minus 10 sine omega t. Okay, so if I wanted to plot what my output was, I could do that. Let's plot it, V out of t. This is simply going to be, there's a negative to it, so it's just going to kind of go the other way, and we have our sinusoid. Now notice that since the magnitude of the amplitude of this sinusoid is between minus and plus 10, we are within the linear region. What I've indicated here with these dashed lines is minus VCC, which is minus 15, and plus 15, which is positive VCC. The output always remains within the bounds of the supply voltages, so we have no problems. We've taken a sinusoid that normally had an amplitude of 2, and we've boosted it. We took an input sinusoid that normally had an amplitude of 5, and we've boosted it with a gain of 2, so that now we have a sinusoid with an amplitude of 10. The minus sign just flips the orientation of the sinusoid in this case. So we are in the linear region in this particular example. But what happens if we change the number? What happens if we change the numbers a little bit? And suppose instead of putting on the input a sinusoid with a magnitude of 5, suppose we put in a sinusoid that had a magnitude of 10. Well, then our output voltage would be equal to minus 20 times sine of omega t times V. And now we have problems, right? Because let's plot what our sinusoid would be. Here's our sinusoid. But now this is normally between minus 20 and plus 20. So the problem is that I've assumed that I'm always in the linear region, but if my output tries to exceed the supplies, then I've now left the linear region and I'm now saturating. What I mean by saturating is the op-amp is now going to basically clip my output so I can never go beyond the supply voltages. So I'm indicating now in red here my supply voltages of plus and minus 15 volts. And this is my hard limit, which is now being imposed by the op-amp. What this means is that over these intervals, I'm not going to get the output that I previously calculated. I'm just going to get minus 15 or plus 15, depending on which limit I'm hitting up against. And it's just going to flatten it. This is known as clipping. It's going to clip the sinusoid so that it never reaches its peak and it stops it from rising. And so now, when I'm in the linear region, I'm going to follow the sinusoid. But once I've exceeded the bounds of my supply voltage, I can't give it any more output voltage. I'm going to be clipped and I'm going to be limited at plus minus 15 volts. And if you were to look at this in the lab on an oscilloscope, you would see a waveform such as the red waveform, which I've just drawn here, which is a clipped waveform. Okay, this is kind of my first introduction of op-amps to give you some things to think about. When we meet in class tomorrow, we'll talk a little bit more about what I've just gone over in this video. And I welcome all of your questions that have to do with either previous material, having to do with first order RL/RC circuits, as well as anything in this lecture. I look forward to seeing you all tomorrow. Take care and have a great day.